All right, today we are diving deep into chaos theory. And look, if you think chaos is just about, randomness and total disorder, you're in for a real surprise. We're about to pull back the curtain on a world of hidden patterns and strange predictability that actually governs everything from the weather to our own heartbeats. So let's start with the big one. You've heard this before, right? It's the most famous image associated with chaos theory. But can a tiny butterfly's wings actually kick off a massive tornado? This question, it really gets to the very heart of the whole thing. Is our world so connected that the smallest little action can have enormous consequences? Well, the answer is a lot more complicated, and honestly, way more interesting than a simple yes or no. When we hear the word chaos, our minds usually jump to a messy room or a crazy traffic jam, just complete, unpredictable randomness. But in the world of math and physics, that is not what chaos means, not at all. It's a whole different beast, one that has its own very specific set of rules. Okay, so let's start by tackling that famous butterfly head-on. The popular idea, it's a bit of a myth, really. It's a powerful metaphor that only captures one piece of a much, much larger puzzle. It's time to separate the poetry from the physics. The real scientific term for this is sensitive dependence on initial conditions. It's a mouthful, I know, but what it means is that in certain complex systems, tiny, almost immeasurable differences right at the beginning can just blow up exponentially, leading to wildly different outcomes way down the line. So the point isn't that the butterfly is causing the tornado. Its little wing flap is just a metaphor for a minuscule change in the starting point of a huge system, like our atmosphere. And the incredible implications of this idea weren't figured out in some grand theoretical vision. Nope. Like so many great scientific leaps, this one came about completely by accident, all thanks to a meteorologist, a pretty primitive computer, and, believe it or not, a simple rounding error. So get this, it's 1961, and a meteorologist named Edward Lorenz is running a weather model on his computer. To get a closer look at a sequence, he decided to restart the simulation from the middle. But instead of typing in the full 6-decimal place number, 0.506127, he just rounded it to 3 places, 0.506. That's a difference of 1 part in 1,000. It should have been totally meaningless. But what happened next literally changed science forever. The two weather forecasts, they started out almost identical, but then they just diverged dramatically. In the end, they were completely and totally unrelated. Lawrence himself summed it up perfectly with this brilliant quote. It really gets to the core of the whole idea. The system is deterministic, right? The present state does determine the future. But here's the catch. You can't cheat. If you only know the present approximately, then you actually know almost nothing about the future. So that single discovery blew the doors open to a brand new field of science. And it was a field that needed a formal set of rules to define what really makes a system chaotic, and not just, random or complicated. And this right here is the central paradox of it all. A chaotic system has zero randomness, none. If you could somehow know the starting conditions with infinite precision, you could predict its future forever. But since we can never measure anything with infinite precision in the real world, long-term prediction becomes completely impossible. It is determined, yet absolutely unpredictable. So for a system to be officially chaotic, it needs these 3 ingredients. First, that sensitivity we've been talking about. Second, it needs something called topological mixing. Just think about how a single drop of dye eventually spreads through an entire glass of water. And third, and this is the craziest part, it must have dense periodic orbits. What this means is that hidden inside all that chaos are an infinite number of repeating patterns. The system never actually settles into one of them, but it gets infinitely close over and over again. They're like these little ghosts of order hiding in the machine. But this is where we find the real beauty of chaos. It's not just a big mess. Within all of that wild unpredictability, there is a stunning hidden structure. And that structure is called a strange attractor. Just think of it as a kind of path that the system is forced to follow. The system state will wander along this path forever and ever, never hitting the exact same spot twice, but always staying trapped within the boundaries of the attractor. It's freedom, but with limits. And there it is, the Lorenz attractor, born from his weather equations. It's maybe the most famous icon of chaos theory, and you can see why, right? It looks just like the wings of a butterfly, bringing our whole metaphor full circle. This is that aha moment. This beautiful, elegant, infinitely complex shape proves that even though the weather from one moment to the next is unpredictable, its overall behavior is not random. It's confined to this incredible underlying order. So this isn't just a bunch of abstract math. Chaos theory fundamentally changed how we see the world around us, from the tiniest scales to the largest ones. Yeah, chaos is literally everywhere. It helps us understand the boom and bust cycles in animal populations, the crazy swings of the stock market, the irregularities in a human heartbeat, and even how a robot learns to walk. It's a fundamental property of just about any complex system. So, what does this actually mean in practical terms? Well, let's circle back to the weather. Because of the atmosphere's chaotic nature, scientists estimate there is a hard physical limit on how far out we can make detailed global weather predictions, and that limit is about 2 weeks. Beyond that, even with the most powerful supercomputers imaginable, those tiny little errors in our starting measurements will have grown so massive that the forecast becomes pretty much meaningless. And that leaves us with this one last fascinating question. Chaos theory showed us that the universe isn't some simple, predictable clockwork machine. But it's not purely random either. It lives in this beautiful, complex space right in the middle. So if the present totally determines the future, but we can never know the present precisely enough to actually predict it, what can we ever truly know about what comes next? Thanks for joining me for this explainer.